Chapter 5: Transformer Construction and Cooling. Transformers are a critical and expensive component of the power system. Due to long lead times for repair and replacement of transformers, a major goal of transformer protection is limiting the damage to the faulted transformer. Some protection functions, such as overexcitation protection and temperature-based protection, may aid this goal by identifying operating conditions that may cause transformer failure. The comprehensive transformer protection provided by multiple function protection relays is appropriate for critical transformers in all applications. The type of protection for the transformer varies depending on the application and importance of the transformers. Transformers are protected primarily against faults and overloads. The type of protection used should minimize the time of disconnection for faults within the transformer and to reduce the risk of catastrophic failure to simplify eventual repairs. Any extended operation of the transformer under abnormal conditions such as faults or overloads compromises the life of a transformer, which means adequate protection should be provided for quicker isolation of the transformer under such conditions. Most transformer failures fall into these categories: winding failures due to short circuits, turn-to-turn faults, phase-to-phase faults, phase-to-ground faults, and open windings. Core faults, core insulation failures, and shorted laminations. Terminal failures, open leads, loose connections, short circuits. On-load tap changer failures, mechanical, electrical, or short circuit overheating. Abnormal operating conditions, overfluxing, overloading, overvoltage. And external faults, which could lead to overloading. If not detected and isolated from the system, catastrophic results could occur, ending in losses to the utility fleet equipment, not to mention the secondary losses that the client may occur and for the utility in terms of revenue. The construction of a transformer in its basic form consists of two coils, at least one high voltage and one low voltage, linked by mutual inductance, and a laminated steel core. In all transformers that are used commercially, the core is made out of transformer sheet steel laminations assembled to provide a continuous magnetic path with minimum of air gaps. The steel should have high permeability and low hysteresis loss. By effectively laminating the core, the eddy current losses can be reduced. The two coils are insulated from each other and from the steel core. The device will also need some suitable container or tank for the assembled core and windings, and to hold a medium such as oil, which the core and its windings can be insulated and cooled. In order to insulate and bring out the terminals of the windings from the bank, appropriate bushings that are made out of either porcelain or ceramics must be used. Generally, the name associated with the construction of a transformer is dependent upon how the primary and secondary windings are wound around the central laminated steel core. The two most common and basic designs of a transformer construction are the core transformer and the shell transformer. In the core type transformer, the primary and secondary windings are wound outside and surround the core ring. In the shell type transformer, the primary and secondary windings pass inside the steel magnetic circuit, the core, which forms a shell around the windings as shown. In both types of transformer core designs, the magnetic flux linking the primary and secondary windings travel entirely within the core with little or no loss of magnetic flux through the air. In core-type transformer construction, one half of each winding is wrapped around each leg or limb of the transformer magnetic circuit as shown. The coils are not arranged with the primary winding on one leg and the secondary on the other, but instead half the primary winding and half the secondary winding are placed one over the other concentrically on each leg in order to increase the magnetic coupling and allowing practically all of the magnetic lines of force to go through both the primary and secondary windings at the same time. However, with this type of transformer construction, a small percentage of magnetic lines of flux flow outside the core, and this is called leakage flux. Shell-type transformers cores overcome this leakage flux as both the primary and secondary windings are wound on the same central leg or limb, which has twice the cross-sectional area of the two outer limbs. The advantage here is that the magnetic flux has two closed magnetic paths to flow around external to the coils on both left and right sides before returning back through the central coils. This means that the magnetic flux circulating around the outer limbs of the core of the transformer construction are equal and one half the total. As the magnetic flux has a closed path around the coils, this has the advantage of decreasing core losses and increasing overall efficiency. The next is a short video on how a simple three-phase transformer bank is constructed. And this video is available on YouTube and was produced by Siemens. Starting with the laminated iron core, which is open at this present time to receive the low voltage windings first, then the concentric high voltage windings with the leads bringing out the connection. The top part of the laminated core is then put on. The leads for the low voltage are connected. Then the top of the transformer is put in place to receive the high voltage bushings and the low voltage bushings, all of which is immersed in the container or tank, which would be ultimately filled with oil. This video is produced by Siemens, as I said, and it's available on YouTube at this web address as you see here. Transformers are usually classified by voltage, starting with low voltage, then going to medium voltage, high voltage, extra high voltage, and ultra high voltage. This table shows the voltage ranges for each classification. Three-wire means a delta connection, and four-wire means a star or a Y connection. And here is what the levels might look like connected into the system, starting at the highest voltage of 380 kV and dropping down to 400 volts. The main source of heat generated in a transformer is its copper losses, or its I²R losses. Although there are other factors contributing to the heat in a transformer, such as hysteresis and eddy current losses, the contribution of the I²R loss dominates all of them. If this heat is not dissipated properly, the temperature of the transformer will rise continually, which may cause damage in the insulation and liquid insulation medium inside the transformer. So it is essential to control the temperature within permissible limits to ensure that the transformers last a long life by reducing the thermal degradation of its insulating system. In electrical power transformers, we use external transformer cooling systems to accelerate the dissipation rate of heat of the transformer. There are different transformer cooling methods available for transformer, so let's look at some of them. The most basic form of heat dissipation in a transformer is the natural air convection, which means the transformer is just standing in air and relies on the dissipation of heat into the air through natural convection means. You'll often see the term AN stamped on the transformer, which means air natural or naturally cooled. These transformers can be naturally cooled with air. The natural convection of the air removes the heat generated by the transformer. As I said, the symbol for this type of transformer is capital A, capital N. ON-AN cooling of transformers. This is one of the simplest transformer cooling systems. ON-AN is oil natural, air natural. Here, natural convectional flow of hot oil is utilized for cooling. The oil will absorb the heat from the transformer windings and core, then migrate to the top of the transformer. It will then flow naturally into the radiators, which will dissipate the heat into the atmosphere by natural conduction and radiation, thereby cooling and moving to the bottom of the rads and tank to start the process over again. In this way, the oil in the transformer tank continually circulates when the transformer is under load. As the rate of dissipation of heat into the air depends upon the dissipating surface of the oil tank, it is essential to increase the effective surface area of the tank. So additional dissipating surfaces in the form of tubes or radiators connected to the transformer tank will do this. ONAF cooling of transformers, which stands for oil natural air forced. Heat dissipation can obviously be increased if the dissipating surface is increased, but it can be made further and faster by applying forced air to flow over the dissipating surfaces. Fans blowing air on the cooling surfaces is employed. Forced air takes away the heat from the surface of the radiators and provides better cooling than just natural air convection. As the heat dissipation rate is faster, electrical power transformers can be loaded more without crossing the permissible temperature limits. The air forcing fans are sometimes switched on and off in stages, providing stage ratings for the transformer. The heat dissipation rate can still be increased further if this oil circulation is accelerated by applying some force. In OF-AF cooling systems, the oil is forced to circulate within the closed loop of the transformer tank by means of oil pumps. OF-AF means oil-forced, air-forced cooling methods of transformers. The main advantage of this system is that it is compact, and for the same cooling capacities, OF-AF occupies much less space. We know that ambient temperature of water is much less than atmospheric air in the same weather conditions, so water may be used as a better heat exchanger medium than air. And that is especially true if there is plenty of water available, which is the case for hydraulic generating stations. So quite often in some of the larger hydraulic generating stations, transformers, as well as some of the generators, have water-cooled radiators that dissipate the temperature away from the equipment. In OF, WF cooling systems of transformers. The hot oil is sent to oil to water heat exchanger by means of oil pumps, and there the oil is cooled by circulating cold water on the heat exchanger oil pipes. OFWF means oil forced, water forced cooling in transformers. This is the case for the main step-up transformers at the Churchill Falls generating station that takes the voltage from the 11 generating units at the station and steps the voltage up to 230,000 volts. The fact that these transformers are located underground means that they want to keep the dimensions at a minimum, so they employ water cooling for the transformers. And of course, there's plenty of water available because it is a hydraulic generating station. This is a cutaway or a side view of the generating station, and you can see the transformers located at about 1,000 feet underground. And the water from the intake is circulated through radiators in the transformers themselves in order to carry the heat away. These are the transformers that are located in the underground facility. Here we see one of them, and indeed not only the water is used to cool the transformer itself, because there's about 33,000 amps flowing in the primary of the transformers. It takes the power from the generating units. Even the ductwork is enclosed. Even the bus, low voltage bus, is in ductwork that is cooled by water as well. Liquid cooled transformers. These transformers have coils immersed in insulating medium, usually oil, which serves multiple purposes. First, to act as an insulator, and second, to provide a good medium through which to remove the heat. Liquid cooled transformers cooling classes went through a major change when the IEEE adopted the standard of a 4-letter designation found on most modern power transformers. The first of these 4 letters designates the internal cooling medium in contact with the windings. O stands for mineral oil or synthetic insulating liquid with a fire point of less than 300 degrees C. K stands for insulating liquid with a fire point of greater than 300 degrees C, and L is insulating liquid with no measurable fire point. The second letter designates the circulation mechanism for internal cooling mediums. N stands for natural convection flow through cooling equipment and windings. F is forced circulating through cooling equipment such as cooling pumps, and uses also natural flow of convection of the windings themselves and isn't necessarily directed. The D is the directed element. It actually stands for force circulating through cooling equipment that is directed from the cooling equipment into at least the main windings. The third letter stands for describes the external cooling medium. A for air, W for water. The fourth letter stands for the circulation mechanism for external cooling medium. N for natural convection, F for forced circulation, such as fans and pumps. Here's an example of what you might find stamped on a transformer, ONAF, which stands for oil, natural, air, forced. ONAN stands for oil, natural, air, natural. And OFAF cooling of transformers stands for oil forced, air forced, and OFWF stands for oil forced, water forced. Unfortunately, a lot of transformers that were built and are still in service today, prior to the IEEE adopting its standard of a 4-letter designation, the ratings may not be found in their full 4-letter designation. In these cases, you will have to use your ingenuity and a little imagination to interpret the cooling ratings, as you will see in the following examples. Here is an example of an older transformer that doesn't use the standard 4-letter designation for the cooling method. In this case, it's multi-rated, and it uses either a 2-letter or a 3-letter designation, which is similar to the 4-letter designation. The first level of rating on the transformer is 50,000 kVA or 50 MVA, which allows for a 55 degrees rise in temperature, but it's the OA designation means that it's the oil and the air is just natural convection used for cooling the transformer, and it's rated at 50,000 kVA. If the next stage of the transformer is to turn on some fans, and you'd have forced air cooling, which would increase the rating of the transformer to 66.667 MVA, and that would allow the transformer to provide that load without rising above 55 degrees C. Next is forcing the oil as well as the air, so that means they've got oil pumps as well as fans cooling this transformer, which would increase the rating of the transformer to 83.333 MVA, and it would allow that type of a load without exceeding the 55 degrees C. You can also raise the output of the transformer temperature to 65, which would allow you to go to 93.333 MVA, and this would be, of course, running the forced air as well as the oil pumps to cool this type of transformer. The mechanical assisted equipment is usually automatically switched on as the operating temperature rises, but it could be operated initiated. In either case, close observation is required, as this expensive equipment is operated close to its rating limits. In any event, protective relaying should take it out if the limits are exceeded for too long. Here is another example of a transformer that's multi-rated depending on the cooling type that's implemented. And again, it's an older type transformer, so it doesn't have the 4-letter designation, but it does have 2-letter designations. Here, the natural convection method, or without fans or pumps, the transformer has 2 ratings at different temperatures, a 24 MVA rating at 55 degrees C and a 26 MVA rating at 65 degrees C. There appears to be 2 stages of fans for this transformer. So the first stage of fans being turned on would allow a 32 MVA rating not to exceed 55 degrees C and a 35 MVA rating not to exceed 65 degrees C. If the last bank of fans is turned on, this will allow a rating of 40 MVA at 55 degrees C and a 44.8 MVA at 65 degrees C. Again, these fans should be turned on automatically. However, if they are watched by an operator, these temperatures will have to be adhered to. And again, ultimately, there is relaying in the transformer that will take it out if the temperatures are exceeded for a longer period of time. Here is a third and our last example. It is a smaller transformer, and it is, I guess, fairly newer because it does have the four-letter IEEE standard designation for cooling method, but it does have a multiple rating as well. It is an ONAN cooling, which is oil natural, air natural, and it has a dual rating depending on the temperature you want to operate the transformer at. It has a 7.5 MVA and should not exceed 55 degrees C, and it should be able to put out 8.5 MVA and should not exceed 65 degrees C. And this ends chapter 5.